one of the things, oh, here comes Ryan. Let me get him here. Okay. And here's Ryan. So the top two and the last are here. Hopefully we can get the other two in soon. Goodness, I forgot what I was going to say now. Hold on. Okay. We are in Chapter 4, higher order differential equations, in 4.1.1, which is preliminary theory, linear equations, and we're in initial value and boundary value problems right now. So that's where we'll be starting from today. Oh, I know what I was going to say. One reason I was a little late getting here is that at the end of the last class, and here comes, I think, Jemanuel. Okay, so let me get Jemanuel in here. Now we got 4 out of 5, so we're just missing James. Hopefully he'll be in. He was here for the previous class. But I can't see if he's here now, so hold on just a minute here. Nope, still no James. Okay. But at the end of the last class, I thought I had everything done, but evidently I didn't stop the recording. I thought I had, I didn't, and when I came back up to get started with this class, there we were still recording that half hour or 35 minutes that I went downstairs to finish eating lunch. So if you do watch the YouTube video from the Cal 3 class, the last 30 minutes or so are absolutely nothing. So just stop watching because I forgot to end that recording. My brain just not with me today. I'm just exhausted, so sorry about that. All right, any questions, issues, problems, concerns besides my incompetence here? Okay, if not, we left off last time, like I said, Chapter 4, higher order differential equations. 4.1 is preliminary theory linear equations, and we're in 4.1.1 initial value and boundary value problems. And we've talked about what the boundary value problems are. This is how a boundary value problem can look. You have a boundary here, a boundary there, and you may even have another boundary in there, but you can have an infinite number of solutions that can go through those 3 points. So a boundary value problem does not uniquely identify a solution. Usually initial value problems will do a lot toward defining a solution. Okay, boundary value problems not necessarily. So here, example 3 is where we're going to pick up today. This is the very bottom of page 120, and it'll go on into 121. And this is aggravating my clip on my thing is just not holding well today, so it keeps falling off. So here's what we've got. Example 3, a boundary value problem can have many, one, or no solutions. So here, if you go back to section 1.1, there was an example there, 9, way back then. We saw that the 2-parameter family of solutions of this differential equation, the x double prime plus 16x equals 0, is this, okay? X equals C1 cosine 4t plus C2 times the sine of 4t. Okay, that is a 2-parameter family of solutions for that differential equation. Now we could verify it. It would be pretty simple to do. We can do that. Let's do it sort of quickly. Well, let's just talk through it. Okay, the first derivative of this would be minus 4 C1 sine of 4t plus 4 C2 cosine of 4t. That's the first derivative. Second derivative would then be minus 16 C1 cosine 4t minus 16c2 sine 4t, and when you add that to, that's your second derivative, then 16 times this would be 16c1 cosine 4t plus 16c2 sine 4t. They add to 0. So sure enough, that is a two-parameter family of solutions for that differential equation. Now, that's without any initial conditions, without any boundary conditions. That's just a two-parameter family of solutions. Okay. Suppose we now wish to determine the solution of the equation that further satisfies this boundary condition. Boundary condition, not initial condition. X at 0 is equal to 0. So when t is equal to 0, x is equal to 0. Right there. Okay. And when t is equal to pi halves, x is also equal to 0. So t equal pi halves, you'd be right there at 0 again. Observe that the first condition, 0 is equal to c1 cosine of 0 plus c2 sine 0 would imply, because sine of 0 is 0, cosine of 0 is 1, so that means c1 has to be 0. For that first condition to be met, c1 would have to be 0. Okay? Now, that leaves you an equation then. X is equal to c2 times the sine of 4t. Okay, but when you put in the second value there, t is equal to pi halves, and do 4 times pi halves, that would be 2 pi. Sine of 2 pi is also 0. So c2 can be any number in the world. Any value c2 would work, because sine of 2 pi is equal to 0. Therefore, this boundary value problem with those boundary conditions has infinitely many solutions. You see 4 of them listed there. Okay, the pink one goes up a little bit, the orange one goes up a little more, the green one goes up quite a bit more, the I don't know, almost it looks orange as well, goes down, it has a negative c2 value. So infinitely many c2s here. Every one of them goes through this position and that position, and it just happens to turn out this position as well. Okay, so that gives you a sum of the one parameter family of solutions, that, because we already determined c1 was 0. Okay, now what if we change our boundary values? Okay, that same initial equation, x double prime plus 16x equals 0, and x of 0 is equal to 0. That's exactly what we had before. But now the next one is going to be x at pi eighths is equal to 0. Okay, now plugging in there, when you put the x equals 0, t is equal to 0, x equals 0. So plug that in here, just like we did before. That says c1 has to be 0, because sine of 4t is always 0, sine of 0 is always 0, and this would be sine of 4 times pi, let's see, where is it? Yeah, cosine of 0 is 1, so c1 would have to be 0. So we get c2 as arbitrary coefficient there. Okay, but then when we put in x, when t is equal to pi eighths, and it's this very same thing here, only now this is a pi eighths, and you plug that in, you get that 0 is equal to c2 times the sine of 2 times pi eighths 4 times pi eighths. Well, 4 times pi eighths is pi halves, and the sine of pi halves is always 1. Well, then you have that c2 has to be 0 as well. Well, then what that produces is neither one of your C's they both have to be 0, so that has absolutely no solution. None whatsoever. The only way you can have a solution is for both the C1 and C2 to be 0. Okay? This one still requires C1 to be 0, but when you apply x at t is equal to pi h to be 0, then that demands that 0 is equal to C2 times pi halves. Well, sine of pi halves is 1. So C2 has to be 0. So your trivial solution, x equals 0, is the one and only one boundary value problem that you can have. One and only one solution, x equals 0. Okay. Now, what if we change again? And this time we say that the same differential equation, same same first boundary condition, same in all three of these, but then this next one says that sine of pi halves is equal to 1. Okay? Well, yuck. This one again produces C1 is equal to 0, just like it did before. But then when you put this in, x at pi halves, right here, that's equal to 1. So 1 is equal to C2 times the sine of 4 times pi halves. Well, that's 2 pi. Well, that gives you sine of 2 pi is 0. You get 1 is equal to C2 times 0. Well, guess what? That's always 0. Always 0. No matter what C2 is, it's always 0. So therefore, that boundary value problem has absolutely no solution. There is no C2 you can put in there that will make that equal 1, because that's what it's saying here. 0 is equal to 1. Not going to happen. So that's an illustration of why boundary value problems do not necessarily, they may occasionally, but do not necessarily define a unique solution. You may have infinite number of solutions, one unique solution, or absolutely no solutions. So just can't count on boundary value problems to get what you need necessarily. Initial value problems typically come out a little bit better. You can still have some issues with them, but they typically come out better. Boundary value problems, you can be all over the place. So let's go to 4.1.2, which is going to talk about homogeneous equations. Time out of a moment here, okay? In the last part of chapter 2, I think it was 2.5, I believe it was, when we talked about certain other kinds of equations that you can get solutions to. We talked about one kind called a homogeneous solution. Now, if you remember that, what that meant, what every term in that differential equation, the degree of every term was the same. Okay? That's one type of homogeneous equation. That's not what we're talking about here. This is going back to the other definition where everything is equal to 0. Okay? Not that they all have the same degree. So a linear nth order differential equation of this form. Okay? Now here's the key word here. Linear. Because remember, the other homogeneous equations we had were not linear, because quite often the x could be squared to 5th power, the 17th power. It could be anything. Not linear. So when we're talking about a linear nth order differential equation being homogeneous, that has a completely different meaning. And here's what we mean by it. And remember how we define those linear equations? Your coefficient function, a sub n of x, for this n here indicates it's just the coefficient function going along with the nth derivative. This n has almost no meaning here. It just identifies this is the coefficient function that goes with the nth derivative. Okay, so a sub n of x, d, the nth derivative of y with respect to x to the nth power, plus a sub n minus 1. Again, that just means it's the coefficient function that goes along with this n minus first derivative of y with respect to x to the n minus first times. And then you step on down a sub n minus 2 of x, the n minus second derivative, blah, blah, blah. Keep going down till you get to a sub 3 of x, y triple prime, plus a2 of x, y double prime, plus a1 of x, y prime, plus a0 of x times y. All that long differential equation, linear differential equation, all these are functions of x alone. These derivatives here only show up to the first power, okay, linear differential equation, and the y is here, y alone, no y squared, no y to 1/3, no fractional or any other exponent, and the y's are only multiplied. Never a y times a dy, never a y double prime times a y triple prime. Can't have that to be linear, okay? So that's going to be linear. If all these things are equal to 0, that's what makes it a homogeneous equation. Said to be homogeneous when the linear equation here is equal to 0. Now, if that same linear equation here, everything's identically the same, except over here, it's not equal to 0. That could be a constant, it could be a function of x, it could be anything. No y's there, no y's at all, because that would then make it probably nonlinear. But if it's only a function of x, which would include constants and stuff like that, that would be a non-homogeneous differential equation, linear differential equation. This is homogeneous when it's equal to 0, non-homogeneous when the g of x is not equal to 0, not identically equal to 0. Now, this one, 2 y double prime plus 3y prime minus 5y equals 0. Homogeneous because every one of these derivatives here and the function y only to the first power. This happens to have constant coefficients, which are functions of x, constants, and this equals 0. That's homogeneous. That's a second order linear differential equation. However, this one, x cubed, no problem there, y triple prime, plus 6y prime, no problem there, plus 10y, no problem there, but that's equal to e to the x, no longer linear. That would have to be a 0. If that were a 0, that would be a homogeneous linear differential equation. If that's not 0 and e to the x is not necessarily 0, this is a non-homogeneous linear third order differential equation. So this word homogeneous in this context does not refer to the coefficients that are homogeneous functions. That was a difference. If these functions here, the a sub n's, a sub n minus 1, if all those had the same degree, that was a homogeneous function, not a homogeneous linear differential equation. Okay, so, and that was in 2.5 like we were talking about. We shall see that to solve this non-homogeneous linear differential equation, this one, number 7, we must first be able to solve the associated homogeneous equation. In other words, the first thing we'll do is set the g equal to 0, come up with a solution for the homogeneous type, and then we will go back and work it out for the non-homogeneous. To avoid needless repetition throughout the remainder of the text, we shall, as a matter of course, make the following important assumptions when stating definitions and theorems about linear equations. Remember the ones way back, okay? These are linear equations, okay? On some common interval I, the coefficient functions, that's the a sub i's, all this a sub n minus 1, a sub n minus, all those functions have to be continuous. And the function g of x has to be continuous. It cannot be piecewise defined. It has to be continuous functions. Okay? Now, the other condition, excuse me, is that the a sub n of x, that very first one, here or here, whichever one it is, cannot be 0 for every x in the interval. Remember, x defines your interval there, your domain that you're dealing with. The a sub n of x cannot equal 0 for any x in that interval. Okay? The reason for that, if that were at any value equal to 0, then this would no longer be an nth order linear differential equation. It would be an n minus first at best. Okay? So you have to have that as another condition. Now, here is where they introduce some more nomenclature. And it's perfectly fine, it's perfectly good. I just don't see a particularly beneficial reason for them to come and start dealing with these operators. They certainly are true, they work well, but I just don't see that you gain that much from them. So in calculus, differentiation is often denoted by the capital letter D, okay? And that D stands for a first derivative, dy dx. So why don't just call it dy dx? Why introduce a capital D for that? Because this is not that much harder to write than that, but they choose to do it. Now that symbol D is called a differential operator, just like dy dx is a differential operator. So there's nothing new here, okay? Because it transforms a, sorry about that, differential function into another function. Now that may be a little vague, so let's pull this up here. Whoa, whoa, here comes James. Perfect attendance today. Way to go, team. So we only missed Kyle in the middle class. I had perfect attendance in the first one, all but Kyle in the second one, and then perfect attendance today. I'm so glad for y'all. Okay, so, oops, I thought I let him in, but it didn't seem to take. All right, so what I'm going to do is take this and move it up here again. Okay, now, that symbol D, what we're talking about, James, we're on chapter 4, higher order differential equations, 4.1, preliminary theory, linear equations, and we're in 4.1.2 on page 121, just about to move to 122. In fact, we are in the process of moving there right now. Okay? And we're just talking about a differential operator, which, as I was saying, I find no great benefit in using it, but they love to use it. Okay? It basically is another way of saying dy dx, just call it capital D of y. Okay? So why? I don't know. It's okay. So here's the, for example, d of cosine 4x would be d by dx of cosine 4x. That would be minus 4 sine of 4x. That's all it is. So why call it d? Why not call it d by dx? Okay, I don't know. This one, d of this would be 15x squared minus 12x. It's just taking a derivative. Why introduce a new terminology? We already have plenty of terminologies for taking derivatives, but they like to do it. Now, higher order derivatives can be expressed in terms of d in a natural manner. The d by dx of dy dx would then be d2y dx, which would be d of dy, because this is dy, this is another d of that dy, and so they call it d2y, okay? Which I guess is a little easier to write than this is, but what's the point, okay? Now, in general then, the nth derivative of y with respect to x to the nth would be d to the nth of y. It means the same thing, the nth derivative. What's the advantage? Not a lot. Okay. Okay. It represents a sufficiently differentiable function. Okay. y represents this sufficient. In other words, you have to be able to differentiate it in order for that to make sense. Okay, so polynomial expressions involving d, such as d plus 3, that would be a derivative of y with respect to x plus 3 times y. I mean, you just put a y after it. This is second derivative with respect to x squared of y plus 3 times the derivative of x with respect to y with respect to x minus 4 times y. Okay, you just use this. This would then be 5x cubed times the third derivative of y with respect to x cubed minus 6x squared times the second derivative of, yeah, you just keep doing. It just is expressing derivatives as if they were polynomials in the operator d. So maybe in that sense it does seem to be a little easier to write, yeah, because you don't have all the d by d's and squares and cubes and stuff. That is a little easier to write, but what's the point? Okay, these are also differential operators. In general, we define the nth order differential operator or polynomial operator, remembering, understanding it is a differential operator. Okay, now here they introduce a new one. Okay, why? I don't know. This new operator is L, and that basically stands for a linear operator, and that would be a sub n of x times your d, the nth derivative of your function y, okay, plus your a sub n minus 1 of x times your second, or your n minus first differential operator. And then step on down till you have, oops, I don't know what's happening here. Maybe I hit something. Let me see. Did someone come out and come back in? For some reason, I can't get it to show up. Kira must have gotten bumped out and had to come back in. Sorry about that, Kira. I didn't see it when it happened. Okay. I hope you didn't miss too much, did you? Okay, good. All right. Now, so it's just another way of, it's a shorthand, basically, is what it is. You've changed this differential operator, the d by d's, okay, into a capital D. Now you take that capital D's and make it into a linear operator, okay, where this is some function of x times your differential operator here and different functions of x carrying on down until you get to the end. As a consequence of these two basic properties of differentiation, okay, this differential operator, the d, operating on some constant times your f of x is going to be that constant times the d operating on f of x. Well, yeah, that makes sense, because derivative of a constant times a function is the constant times the derivative of the function. That goes way back to Cal 1, okay, where c is any constant. Here's the second one. The derivative of the sum of two functions is the sum of the derivatives of the two functions. It's just the simple rules and patterns that we saw before. It's just using this differential operator rather than d by dx. Okay, everything's the same. Now this differential operator L possesses a linearity property, and these are the two linearity properties. D by constant times a function is equal to the constant time d of that function, and the differential of the sum of two functions is the sum of the differentials. So that is what we call a linear combination of the two differentiable functions, is the same as a linear combination of L involving the individual functions. Now, a lot of blah blah blah, and you wonder, what difference does it make? Okay, now if that wasn't enough, let's see how we can complicate it further. Okay, this looks a lot like something we just saw a little bit ago when we were talking about boundary value problems. We saw something that looked similar to this, but it was different. A linear operator operating on some alpha times a function f plus some beta times the function g is going to be alpha times that linear operator operating on f plus beta times the linear operator operating on the function g. So here again, alpha and beta are just constants, and because of this, we say that the nth order differential operator is a linear operator, because you're not introducing any squares, cubes, cube roots, anything else. Everything stays linear. Okay. Now, again, why introduce all this new terminology? It's fine. No reason not to, but it just seems like you get wound up in that and you wonder, what's the point? Okay. It worked just as easily the other way. So let's look at differential equations. Any linear differential equation can be expressed in terms of the notation. Any linear differential equation can be expressed in that notation. They don't say anything about exact equations or other things, just the linear. Okay. For example, this differential equation is y double prime plus 5y prime plus 6y is equal to 5x minus 3. That can be written as, there's your second derivative, d2y plus 5 times dy plus 6 times y is equal to 5x minus 3. Okay. Or pull out the y's. It's sort of like it's a factor, and this would be d squared, but now remember, these are not functions, they're operators. D squared plus 5d plus 6 times the function y is equal to that. Now, using this kind of expression here, okay, using that kind of expression, we can write the linear nth order differential equations 6 and 7, which were their homogeneous and non-homogeneous, as just simply L of y is equal to 0 and L of y is equal to g of x. Okay, what's the big deal? Okay, yes, you can do it. No problem at all. Okay. Now, with that done, they jump another rabbit here and start talking about the superposition principle. We've already hit this a little bit. We're going to hit it some more and keep hitting it, because this is a pretty important feature of linear differential equations. Okay. In the next theorem, we see that the sum or superposition of two or more solutions of a homogeneous linear differential equation is also a solution. This is called the superposition principle. So here's what we got. Now remember, these are homogeneous equations. Let's just say that y1, y2, y3, y4, y5, all the way up to y sub k. So you have k solutions. These are solutions to the homogeneous nth order differential equation that we had back here. I don't know if I can still show it and be on the same slide. Let me see if I can. I don't think so. No, it's off scale. Okay, but it's that equation 6 was your homogeneous equals 0. Whatever that was equals 0. This is solutions for this nth order differential equation on some interval I. Then the linear combination of those, if each of those was a solution, then any linear combination of them would be a solution. Y is equal to C1 times the first one, plus C2 times the second one, plus C3 times the third one, all the way up to CK times the kth one. That will also be where your C sub i's are 1 through k, and they are arbitrary constants. They're also solutions for that differential equation on that same interval. Okay, now they do a little proof here, and they use their linear operator, which is fine, except they really haven't done many proofs with them. But we prove the case with k is equal to, let L be a linear, the differential operator, linear differential operator that we had up above. Let y1 of x and y2 of x be solutions of that differential equation, L of y is equal to 0, then if we define y is equal to c1 y1 plus c2 y2, a linear combination of those two, then by the linearity of L, we have that this thing here is L times this plus that, because your y is c1 y1 plus c2 y2. So the linear operating on that is that. Well, that is c1 L of y1 plus c2 L of y2. And remember that this was a solution. That was a solution. Both of those are solutions. So the sum is a solution. So that seems pretty, I guess, a little straightforward, but it's there. That's what it is. Now, if you're wondering where is this going, it's going to come out to something that's pretty good. So let's look at a couple of corollaries to this theorem here. A constant multiple of y, that would be c1 times y1, okay, is a solution of y1 of x, of a solution y1 of x of a homogeneous solution is also a solution. So if nothing else changed, just a multiple of a solution is a solution. And a homogeneous linear differential equation always possesses the trivial solution y is equal to 0. Now this is for homogeneous. Remember, if this thing right here is equal to 0, then there's no way that if y is equal to 0, y prime is equal to 0, y double prime is equal to 0, if all those things are 0, which they would be, then that would satisfy the homogeneous equation. So every homogeneous linear differential equation has at least one solution. That would be the trivial solution. Okay? Now, they may have more, and if they do have more, then the linear combination of them will also be a solution. Okay. So let's see if we can do example 4. Okay? And I think I'll just go to the white page. Okay? Now it looks like we've lost somebody, have we? Yeah, we have. We had all 5 people here, but now we're missing. Goodness, who are we missing? Is Kara? No, Kara's still here. Jemanuel? No, Jemanuel's still here. Jesus is still here. James is still here. Who are we missing? Oh, Ryan. We've lost Ryan. Okay. Hopefully he'll be back. Okay. So let me minimize this and go back to the whiteboard. Okay. Now, I need to move y'all around a bit. Okay. So I'm going to move us to the right hand side. Move my taskbar to the top. Move the whiteboard as far to the left and up as possible. Okay. Now let's do example 4. This is, by the way, top of page 123. Now let me get my pen. So here's some functions. Where is my pen? There we go. All right. Here's a function y1 is equal to x squared y2 is equal to x squared log x. Okay. Now they say these are both solutions of this homogeneous linear differential equation. That's supposed to be solutions that ran together. X cubed y triple prime, yuck, x cubed y triple prime minus 2xy prime plus 4y equals 0. Okay. Now they claim those are both solutions of this homogeneous differential equation on this region. Get out of there. And this will be from 0 to infinity. Now we're going to do a timeout right here for a moment. Okay? And here's what the timeout is all about. Okay? Number one. Notice that x cannot equal 0. Of course it can't, because if x is equal to 0, the coefficient function would be 0. That can't happen. It cannot happen. So x cannot equal 0. It could have been anything negative, I think, as long as it's not 0, or anything positive, as long as it's not 0. They happen to choose the interval that contains positive numbers. Doesn't matter which, but that's what it is. Okay? Now, there's a part of me that wants to show that these are solutions, to prove that they are. Okay? So let's do the first derivative of this one. First derivative would be 2x. Second derivative would be 2. Third derivative would be 0. Okay? So that looks okay. That would be 0. Okay? Now, let's do the same thing here. Now that would be a product rule. Okay? First derivative would be 2x log x plus x squared over x, which would be x. Okay? I don't think I want to go through all this. We'll just take their word for it. They didn't say verify it, but I thought maybe it would be fairly easy to do so. Okay. Now, they're telling us those are both solutions. Now, what we've just claimed is this, that the linear combination of them should also be a solution. So C1 x squared plus C2 x squared log x should also be a solution. Let's just call it y, okay? And that's also a solution for that differential equation, okay? Now, okay? That's all they're doing, okay? They just said if those two are solutions, then the linear combination is a solution. They didn't ask us to verify it or anything else, but it will be true. Okay? Because you know, if that's a solution, a multiple of that will be a solution. If that's a solution, multiple is a solution. And if the sum of two solutions is a solution. Okay? That's all they did there. Now, frankly, that wasn't much of an example, was it? But let's go to the next thing here. Okay? And I don't know if we need these both together, but that took so little time to write. Let's do this one. Okay? Okay? Here's a function. Y is equal to e to the 7th x. Okay? Now they claim that is a solution of, I put 2, but of y double prime minus 9y prime plus 14y is equal to 0. A homogeneous linear differential equation. Okay. Now, this one is pretty easy, I think, to verify. Not that we have to, but let's just do it. It's going to be easier than that one was. Okay, y prime would be 7e to the 7x. Okay, y double prime would be 49e to the 7x. Okay, plugging this in, that would be 49e to the 7x minus 9 times that would be minus 63e to the 7x plus 14 times e to the 7x. And they claim that's equal to 0. Let's see if it is. 49 plus 14, sure enough, is 63 minus 63. Yep, that adds a 0. So absolutely, this is a solution for that differential equation. Okay, that was pretty easy to check. Okay, so we also know this, and again, this isn't very earth-shattering. Y is equal to C1 e to the 7th x is also a solution, because all you have to do is take the derivatives there, you get a C1, you get a C1, and everything adds up just the same as before. Okay, also a solution. For various values of C, we see that y is equal to 9e to the 7th x, y is equal to 0, y is equal to minus, you could just pick any value for C, okay? And frankly, I don't see why they're focusing on this, but it certainly is true. What if that C, this C right here, I'll put C1, they just left it as C, okay? What if that C were 9, okay? What if C was equal to 9? Okay, then y is equal to 9e to the 7th x would also be a solution for that differential equation. What if that C was equal to 0? Okay, y is equal to 0. Well, that's also a solution. If the C would now be 0, this would be 0, that would be 7 times 0, this would be 49 times 0. Add those together, you get 0. Okay? And y is equal to minus the square root of 5, why not? E to the 7th x. Okay? Well, if you were to do that and carry it on through and take the first derivatives and stuff, all you're doing is multiplying by root 5. And everything that worked here would work again. So to me, it's almost any constant you put there. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter. If it's a constant, put it in front, you're going to have a solution. Okay. Now, let's go back to the text. I'm sorry, I'm going to have to. Well, not have to, but I definitely want to. I need a little something. I'm losing it rapidly here. Hold on just a moment. I hate doing this in class, but I almost... I think I told most of you before, I don't know if all of you were here before, my treatments went really, really well last week, Thursday and Friday, but I can almost guarantee you that I'm more anemic now than I was before, because the monoclonal antibody not just knocks out the white cells, which I'm sure it did, I mean big time. I could just sense that the battle was going on inside. It was really knocking them out. But they always knock out a few red cells as well. So I'm more anemic now than I was before, but I'm in better shape than I was then. Okay, now let's move on to linear dependence and independence. These are really important terms. Some of you are in linear algebra. You're going to be hitting them all over the place there as well. So these things all tie together really really well. Okay, and they're talking about the same thing, so it's nothing new. So the next two concepts are basic to the study of linear differential equations, and frankly any linear equations. And here's the definitions. Definition of linear dependence and independence. If you have a set of functions, f sub 1, f sub 2, f sub 3, f sub 4, all the way up to f sub n. They're all these functions, n functions, okay? They are said to be linearly dependent on some interval I if there exist constants c1, c2, c3, c4, all the way up to c sub n that are not all zero, such that that linear combination of those functions, c1 f1 plus c2 f2 plus c3 f3 plus c4 f4 plus all the way up to c sub n f to n, if you can make that equal to 0 with different choices, at least one choice of c's, that they're all not 0. Okay, certainly if all the c's were 0, that's got to be true. But if you can make it true with not all the c's equals 0, for every x in that interval, if that set of functions is not, that's a linearly dependent set. If the set of functions is not linearly dependent, it has to be linearly independent. So in other words, if you can't come up with a set of c's that's going to make that true without all the c's being 0, then that's a linearly independent set. If you could come up with some combination that not all the c's could be 0 and you make that equal 0, that means they're linearly dependent. So, in other words, a set of functions is linearly independent on some interval I if the only constants, linearly independent, the only constants for which that combination would be equal to 0 is if every one of those c's is equal to 0. If you can come up with just one of those not equal 0, or a few of them not equal 0, then it's linearly dependent. But if there's no way you can get that to equal 0 without every one of them being 0, you're linearly independent. Okay, now they seem to like this as an example, and it's a perfectly fine example. Okay, it just seems like there could be some that would be a lot better. All right, let's say we have two functions, f1 and f2. If the set of functions is linearly dependent on some interval, then there are some constants, c1 and c2, that are both not 0, such that for every x on that interval, c1 f1 of x plus c2 f2 of x is equal to 0. Okay? For c1 and c2 not both equal 0, that would be, you could make this become 0. Some linear combination becomes 0. That would mean they're linearly dependent on each other. Therefore, if we assume that c1 is not equal to 0, it follows that f1 could be written as subtract c2 f2 from both sides, divide by c1, as long as c1 is not 0, okay, then you have f1 is equal to a linear combination of f2, because c2 minus c2 over c1 is just a number, okay? C1 cannot be 0, so negative C2 over C1 is just a number, and that means they are multiples of each other. That is, if a set of two functions is linearly dependent, then one function is simply a constant multiple of the other. Okay. Now if you have 5, 10, 15 of them, you won't be able to see them. But if you only got two, yeah, one of them is going to be a multiple of the other every time. Okay. Conversely, if F1 is equal to C2 F2 for some constant C2, then multiply the left-hand side by -1 and add it to this, and then it will be equal 0 for every x in the interval. Okay. Hence, the set of functions is linearly dependent, because at least one of the constants, for instance, C1 equal -1, is not 0. Okay. They're just saying everything round and round and round about. Okay. We conclude that a set of two functions, F1 and F2, linearly independent when neither function is a constant multiple of the other one. Okay. Now here's an example. F1 could be the sine of 2x. F2 could be sine of x times cosine of x on some interval. Now, guess what? F1 sine of 2x, F2 sine x cosine x, they are linearly dependent on -infinity infinity, because sine of 2x is twice the sine of x times cosine x. So that's a multiple. Okay. This is a trig identity. Okay. And because this is a multiple of that, that must be a linearly dependent set. Okay. On the other hand, the set of functions f of x, f1 of x equal x, and f2 of x equal absolute value of x, okay, they're linearly independent on some interval -infinity infinity. And they say looking at this figure should show that. Okay, because this is the function y of x equal x, f equal x. Okay, this is f2, absolute value of x. There's no way that this is a multiple of that, or this is a multiple of that. Piecewise defined, it almost comes out being that way, but not for sure, because you can't have it true on the right and on the left at the same time. If you just dealt with the left-hand side, yeah, that would be linearly dependent. Or just the right-hand side, that would be linear. It's the same. But to have both of them there, nope, can't do it. Okay. Because the quotient of F2 divided by F1, this is -x for x less than 0, x for x greater than 0, and this would be this. So it's either -1, the ratio would be -1 or +1, could never be both. Okay. Now this is a lot of blah, blah, blah. Okay. Let's move on to example 5. Okay. Goodness, I'm running out of energy. Let me take another swig. Okay. Here are two functions. f1 of x is equal cosine squared x. f2 of x is sine squared x. Okay. f3 of x is secant squared x. f4 of x is tangent squared x. Okay. They say this is a linearly dependent set of functions on this interval. And why is that true? Well, let's go to the whiteboard. Okay. I think I'm going to have to move y'all out of the way to get to the whiteboard. Well, I didn't have to, but I'm going to ultimately need to. Let's see, we still don't have Ryan back, do we? I don't see that he's back. Let me clear this out of the way. And here were our four functions. Example 5, bottom of page 123. Here's your f1 of x. F sub 1 of x is equal to cosine squared x. F sub 2 of x is equal to sine squared of x. I'm sorry, the pen writes so weirdly sometimes. F sub 3 of x, this is so aggravating, is equal to secant squared x. Goodness gracious, this is such a pain in the neck. Okay, and f sub 4 of x is equal to tangent squared x. Okay. They claim that's linearly dependent on this is such a pain in the neck. Linearly dependent on the interval minus pi halves to pi halves. Okay, now first let's look at our interval there. It's got to be that way because secant and tangent, and secant squared and tangent squared, but secant and tangent are not defined at x equal negative pi halves or pi halves. So you have to have some interval where they're defined, and this certainly is. Okay, sine and cosine defined everywhere, so their squares are defined everywhere. No problem there. Okay, now how do we know these are linearly dependent? Well, I'm just going to point something out to you. What is cosine squared x plus sine squared x? Anyone know? I hope you do. 1. Okay. Now, let's do another one. 1, let's do tangent squared x plus 1 is equal to secant squared x. Now how do we get that? If we divide everything on both sides of this equation by sine squared x, you get, no, by cosine squared x, this will give you a 1, this will give you a tangent squared x, and this will give you a secant squared x. So you know that's true. Okay? So then we also know from here that if you were to plug in and say, I'm going to rewrite them this way, sine squared x plus cosine squared x, we know that's equal to 1, plus, okay, here's something I'm going to do now. I'm going to subtract 1 from both sides and subtract secant squared x from both sides. Okay, so then this would be, this adds to 0, these add to 0, and this would be plus tangent squared x minus secant squared x. What would that equal? Well, this part equals 1, this part equals minus 1, and these two add to be 0. So guess what? We've come up with a linear combination of constants, not all equal to 0. Certainly if every one of these was 0, 0 here, 0 there, 0 there, 0 there, that would be equal to 0. But look, we've got some that they're not. Coefficient of 1, 1, 1, and negative 1, that gives you a 0. Linearly dependent. Okay? And that's what they were gunning to. Okay? So I'm having trouble seeing this. So when C1 equals C2 equal 1, C3 equal minus 1, and C4, and remember the C3 was the secant, okay, squared, and C4 was 1, you now have some linear combination of those functions that indeed equals 0 without all the coefficients equaling 0. Okay, now we got 4 minutes left. Let's see what we can get done back on our text. Okay, so there we showed, now let me move these y'all out of the way again. Okay, so here's what we just found. We used these coefficients and we found that equals 0 without all the coefficients equaling 0. Now, okay, a set of n functions, f1, f2, f3, f4, up to f sub n, is linearly dependent on some interval I if for at least one of the functions can be expressed as a linear combination of the remaining functions, then it's linearly dependent. For example, if these three functions, f1, f2, and f3, are all linearly dependent on some interval I, if at least one of those functions is a linear combination of the other two. So in other words, let's just say that this f3 would be some combination of c1 f1 plus c2 f2. Now if that's the case, then guess what? c1 f1 plus c2 f2 minus c minus f3, that would be equal to 0. It would have to be, okay? And therefore, that is some equations, coefficients, that not all equal to 0 would produce a linear combination that was equal to 0. So that would be linearly dependent. Okay, let's look at example 6 here. Let's see if we can get this one done pretty quickly. Okay. I doubt it. Okay, I don't think we're going to get this done in 2 minutes. Okay, so what we'll do here is pause for a moment here. Sorry about this. Okay, and we will pick up, I need to find my eraser here. We will pick up with example 6 next time. Okay. Now, homework exercises here would include any of the odds 1 through 3 that are in the back of the book. You can do those. These are on page 130. Either 5 or 7, if they're in the back of the book, do those. Number 9, if it's in the back of the book. Number 11, if it's in the back of the book. Number 13, if it's in the back of the book. Those were all from 4.1.1. Okay, from 4.1.2, the ones we're just working with, any of the odds 15 to 21, I think you can do. And I think we'll just hold off 23 to 29, and we'll do those when we finish this section, 4.1.2. So those are the homework exercises there. And that did run us right out of time are there any questions? Now, again, today was sort of a lot of blah, 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 talking about stuff. This is going to get, what we're going to do now is going to be a lot more practical than just the blah, blah, blah we were talking about before. This one is going to be sort of fun to do. This one gives us a certain way to solve some equations. So any questions? Okay, we'll stop the sharing then, and if there's no further questions, none, we'll end the meeting and we will pick up on Wednesday with on page 124, example 6. Okay, take care folks, we'll see you Wednesday. Bye-bye.